Good morning, everyone. So let's start the day with a session on boomerangs. We have three papers. And the first one is improve search of boomerang distinguishers for generalized facial and applications to warp. And this is a work by Jinhao Zhang, Lin Tan, and Hongxu. The talk will be given by Jinhao.
Thank you for your introduction. Hello, everyone. I'm Xinhao Zeng from Zhengzhou, China. The title of our paper is Improved Search of Boomerang Distinguishers for Generalized Fiscal and Application to Warp. So I'll introduce our work in the following parts. So firstly, I'll introduce boomerang distinguisher and sandwich distinguisher. So boomerang attack, proposed by D. Wagner in 1999, is an extension of differential character analysis. So suppose there's a upper trio in E0 with probability P and lower trio in E1 with probability Q. With these two differential trios, we can get the entire probability of boomerang distinguisher, which is square of PQ. So in 2014, Dunkman et al. Proposed the sandwich distinguisher to formulate the dependency between the upper and lower differential trios. Suppose the probability of the middle part is R, and that of the sandwich distinguisher is R times the square of PQ. To compute the probability of EM more detailedly, in 2018, Sid et al. Introduced the trio of BCT. But later in 2020, Bokro et al. Found that this framework might not fit to fiscal structure, and they extended this framework to FBCT. And the following three tables are the variants of FBCT, which can handle more circumstances in EM. Finally, I'll briefly introduce warp. Warp proposed by Banik et al. In 2020. It is a 128 block lightweight block cipher with 32 branch generalized fiscal structure. It will propagate 40 flow rounds with one partial round. So about our motivation, we found two type of models to search for boomerang distinguishers. The first one comes from DeLoan et al. in FSE 2020. So their model used the BCT framework to the whole cipher and has high precision, but we think it may cost too much. And later in 2022, Lolliman et al. Introduced this model to fiscal structure and applicate their model to warp. The second one comes from Hedpo et al. Their model based on the number of active S boxes, and in 2022 they introduced their model to SPN structure to fiscal structure. And their model is easy to use, but we found it might find the optimal distinguishers. So our motivation is to combine these two models together to get an improved model to search for boomerang distinguishers for generalized fiscal structure. And with the usage of our model, we improve the boomerang distinguishers and rectangle attacks on round reduced warp. So our model is mainly based on the structure of Hadpo et al.'s model. So I will introduce this for you. So their model is divided into the following 4 steps. The first step, they divided the target cipher into 3 parts, just like the structure of sandwich attack. And they encode the different parts with different ways. Then they define some binary variables to indicate the activity of S boxes. Their objective function means they just use the number of active S boxes in E0 and E1 and the common active S boxes in EM to estimate the probability of truncated boomerang trails. In the next step, they instantiate the differential trail in E0 and E1. In this step, they'll compute the cluster effect, which is just compute all the trails in the same inputs and output differences. Next step, they compute experimentally with the boomerang probability of EM with the output difference of E0 and the input difference of E1. In the final step, they compute the entire probability, and the boundaries of EM may need to adjust for obtaining more accurate estimates of the boomerang probability. So the way they count the number of active S box is very naturally, but we found it may not find out the optimal distinguishers. In fact, in our paper, we present 2 distinguishers. The first one comes from their works, and the second one comes from the model comes from our model that we will introduce later. So the two distinguishers have the same number of active S boxes in E0 and E1, but in EM, the first one has 3 common active S boxes, while the second one has 4. With the previous analysis, we will think that the probability of distinguisher 1 should higher than distinguisher 2, but in fact, we have distinguisher 2 is higher than distinguisher 1. So to analyze the reason, we present the 2 formulas to compute the boomerang probability of EM by using the FBCT structure, FBCT. We note that for the first formula, there's more DDTs which is come from the S box just active in one of the 2 differential trails. So, with the technique of boomerang switch, this kind of S box will not cause probability when the boomerang return, but it do play a role in differential propagation. So what we do is to research the impact of the S box just active in only one of the 2 differential trails on the boomerang probability. So with the idea of De Lorentz model, we classify the S boxes in EM more detailedly. The first one is full active S box, which has non-zero differences both in the upper and lower differential trails. This is different from the common active S box, which include 0 difference. The second one is semi-active S box, which has non-zero difference only in one of the upper and lower differential trails. And in semi-active S-box, we define another S-box, which is constraint S-box. The output difference of this S-box will influence other active S-boxes in EM. So, for example, in the following in this figure, we can see for S1, suppose the states with blue and red are all non-zero differences. So for S1, we can see the input difference in the upper and lower differential trio are all non-zero. So S1 should be a full active S-box. And for S0 and S2, it has only non-zero difference only on one of the two trails. So they are semi-active S-boxes. And note that the output difference of S0 will be the input difference of S1 in the upper trail. So which means this S-box will affect the input difference of an full active S-box. So we call S0 a constraint S-box. The final one is free S-box, of which the input difference can take all possible values, including 0. And we can divide this type of S-box into L-free and U-free. So, for example, in this figure, the gamma I and delta I are all non-zero difference. For S0 in the upper trio, we can see its input difference is non-zero, but in the lower trio, its input difference comes from the XOR of two non-zero values. So we say the input difference of S0 in the lower trio is free, and we call S0 is an L-free S-box. So with the define of these active S-boxes in EM, we construct our MILP model with some binary variables, just like Ethel's work. So for the active S-boxes in E0 and E1, we use the same variables like them, and in EM we just use some variables to indicate the tables they use, the active S-box use. And our model is mainly about the active S-boxes in E0 and E1, and the tables the S-box used in EM. So applicate our model to WARP, we get better results in plenty of rounds. And we also apply our model to twine and L blocks, which also get some good results in some of the rounds. We also use the distinguishers we searched for the rectangle attacks on round reduced ROP. Firstly, with the usage of our 21 round boomerang distinguisher, we improve the rectangle attack on 26 round warp, which is better than the best known 26 round rectangle attack on warp on this cipher. Secondly, we employ the probabilistic extension proposed by Song et al. based on the same 21 round distinguisher, we mount the first rectangle attack on 27 rounds warp. So in our paper, we revisit Hetpo et al.'s model, and we found that it just it just haven't considered the semi-active S boxes. We classify the S boxes more detailedly and improve the model of searching boomerang distinguishers for generalized physical structure. And with the use we apply our model to warp and improve its boomerang distinguishers in plenty of rounds. Finally, with the usage of our boomerang distinguishers, we improve the rectangle attacks on round reduced warp. Thanks for your attention.
Thank you. So we have some time for questions. And do we have questions in the room? Yes.
Thank you so much. Thanks for the nice presentation. It was really impressive. Due to the similarity between boomerang and differential linear, do you think if you apply your method to differential linear, you will be able to get a better result in differential linear also? Because we applied the same method to differential linear in Crypto 2024, and I think if you apply this method to differential linear, you will be able to get better results maybe. Did you think about that?
We've considered about actually we've considered about this question, and we think it might get used, or it might get used in the also in the differential linear attack.
Okay, I think it's a good future work. Yeah.
Yeah.
Thanks for your presentation.
Thank you.
So do you have other questions? Yeah.
Thank you for the presentation. A quick question. Which of the attacks have you verified? Because some of that, I know that the 2 to the minus 100, you cannot verify the boomerangs, but did you verify the boomerangs with probabilities 2 to the minus 30 or 2 to the minus 24?
I beg your pardon, please.
Have you verified any of the boomerangs that your tool has found? Did you experimentally took plain text pairs with the required input difference, encrypt them, XOR the output difference, and decrypt to check whether the probability of the boomerang is as your tool expects?
Okay, so the results of our in this table, we do some experiment test with the probability R and P and Q. And we just use the formula of the probability computation of the sandwich distinguisher.
But did you verify the full probability of the full boomerang, not just parts of it? That's my question.
Actually, we didn't do it for the full boomerang. We just do it for the different parts.
Thank you very much.
Thank you.
Okay, we have a final question in the room. Maybe I will ask the final question. So in your work and presentation, you focused a lot on generalized crystals and with the application to warp. But do you think that your observations could apply also to SPN ciphers?
So we just apply our model to the generalized crystal because as we use the semi-active S boxes, it its impact on the boomerang probability will be weaker than in the SPN structure and the Pfister structure with less branches.
I think. Thank you very much. So let's send the speaker again.